I've been talking about doing calculations in quantum mechanics applied to spin-1 particles and the spin states of spin-1 particles. In particular, in this video, I'm going to talk about expectation values and how you calculate the expectation values for particles given some earlier knowledge. But let me start by giving you the background, because to save some time, I'm going to build directly on some results we did earlier when I was calculating direct probabilities. The specific spin-1 state I'm looking at, and I don't know if this is a Z boson or some atomic nucleus with spin-1 or what, I'm looking at a particle in the state psi, or ket psi, is 3i over 5 times the 1, 0 spin state. That's total spin 1 and Z component 0. Z basis is our default basis. Minus 4/5 times the 1 minus 1 state. That's our psi. We're assuming we have a particle in that state, and we want to know expectation values for that particle. Now, in a previous set of calculations, in a previous video, I did a bunch of calculations of probabilities and of some data for this. And in particular, I calculate out that we know that for any spin, Z component of spin measurement, or any component of spin along any axis for a spin 1 particle, the only possible values we can get are plus h bar, 0, and minus h bar. Those are the only values that can possibly turn up. And for our particular state here, I worked out last time that the probability of getting plus h bar as the Z component of spin is 0. And that's because there's no 1, 1 component in this state. The probability of getting 0 as our Z component of spin is 36%. And that came from taking the 1, 0 state, and its coefficient was 3i over 5. The absolute square of that is 0.36, 36%. Similarly, the probability of getting minus h bar for this particular state is just the minus 4/5 coefficient, absolute squared, comes out to be 0.64, 64%. We calculated that last time. Also last time, we did some more sophisticated calculations. We said, hey, what about the y components of spin? We don't just have it written out in the y basis. How do we do that? I won't go through the details, but last time we worked out probabilities. We found that there was almost a 68% chance of measuring plus h bar. We found there was a 32% chance of measuring 0 for the y component of spin, and a 0.06% chance of measuring minus h bar as our y component of spin. And those results ultimately come from the following amplitudes. I have over here, for reference, some details about the matrix representations of the 3 y spin states, 1, 1 in the y-axis, 1, 0 in the y-axis, and 1, minus 1 in the y-axis, in the Z basis, so written as combinations of Z states. And these are the matrix representations. And the last thing, I also wrote down the bracket representations of these things, translating that into that language. Whatever you do, we calculated these 3 amplitudes, these 3 Dirac brackets. The 1, 1 y state, bra, meeting the psi ket, gave us this value, this 0.82. 1, 0 y with psi gave us a negative 0.56, and the 1 minus 1 y with psi gave us a negative 0.02, and those each squared give us those 3 results that we had earlier. So that's the source of those things. We've done these calculations. I'm not going to redo them now. I want to have them here just for reference so we can refer back to this and talk about our expectation values and how we're going to do those calculations. So I said I wanted to calculate an expectation value. What is an expectation value? Well, remember, the intuition is this weighted average of possible results. And the weighted average, the idea is that if I had a million of these things, a million particles in the same state, and I measured the Z component of spin for each one of them, what would be the average measurement I got? And so weighted average, it's weighted by the probabilities. Essentially, I can say that the expectation value of SZ, and remember, expectation values are for a particle in a particular specified state. It's not a general thing, it's for this particular state. SZ, that expectation value is going to be the first possible measurement, h bar, times the probability of getting that measurement, SZ equals plus h bar, plus the second possible measurement, 0, times the probability of getting SZ equals 0, plus the third measurement, third possible outcome, is minus h bar times the probability of getting SZ equals minus h bar. That's what we do. That's what we find the expectation value. Now, for our particular case, these come out to be very easy because the first probability is 0, and the second expectation value is 0. So this whole thing is just the third term. The expectation value winds up being minus h bar times the probability of getting minus h bar, 0.64, and that's my expectation value. That's the whole thing. That seems, once I've done this work, that's the easiest way to do it. And often if you have your state written in that basis that you're doing expectation value, if you're written in the basis of the operator, basis of eigenstates of the operator whose expectation value you're measuring, cool, that you just do this. This is the most straightforward way of doing it. But let me point out the other ways that we can do this. The two other ways of calculating the expectation value that are also useful ways of doing it that are generalized better if you don't have these calculations already done. So one of them, the other thing about expectation values is that you can always write it as, so that was my first method. My second method is to say that this is equal to the psi bra multiplying the SZ operator acting on the psi ket. So I can. This is a way of writing an expectation value. Psi SZ hat psi is a way of writing this. And what's that do for me? Well, why is that useful? If I plug in my definition, psi bra SZ hat, well, write in my SZ hat, keep that there, and then my state over here, I can put the details of my state definition in. I'll put in 3i over 5 times the 1, 0 state minus 4/5 times the 1 minus 1 state. I just put it in my definition. And at this point, because these are eigenstates of my SZ operator, I know exactly what's going to happen to them. My SZ operator is going to come in and distribute through these parentheses. And when it does, it's going to go right through each coefficient, each numerical coefficient. I apologize for the banging noises, by the way. This is construction of the building. It's going to go through that coefficient, going to pass right through the 3i over 5, and it's going to give its eigenvalue when it acts on its eigenstate. That's the whole point. It gives its eigenvalue. Well, when SZ acts on 1, 0, it gives me a 0 times the 1, 0 state, 0, right? And then minus 4/5. Again, I'm distributing the SZ operator through. When my SZ hat comes through and hits that state, hits that eigenstate, it gives me the Z component of spin, minus h bar. Gives me that minus h bar. And so that's what I get from that calculation. And this term obviously goes to 0. So now I'm going to put in the bra version of psi. Remember, it's the conjugate transpose in matrix form. I take the complex conjugates of the coefficients to get the bra form. And so this left-hand side becomes minus 3i over 5 times the 1, 0 bra. And then just the same old minus 4/5 times the 1 minus 1 bra. And all that's left over on this side is minus 4/5 times minus h bar is plus, yes, I left out my ket. Sorry, left out my ket. 1 minus 1 ket. That was terrible, left out my ket. Okay, 4/5 h bar times 1 minus 1 as a ket. This is what I have left. And at this point, again, I know how bra-ket notation works. I put the brackets together. I distribute this term into each term of the previous parentheses. When the 1, 0 meets the 1 minus 1, those are orthogonal states. So they'll cancel out. It'll give me 0 contribution. When the 1 minus 1 meets the 1 minus 1, they're normal. That's a normalized state. Its bracket with itself has to be 1. And so I wind up getting, I get negative 4/5 from here times positive 4/5 h bar times 1, my normalized state. Or in other words, negative 16/25 h bar, which is the same as negative 0.64 h bar. So I get the same answer doing it that way. I get the same answer, and you can kind of see just looking at this how we get the probabilities coming through here, right? The probability that mattered was just the 1 minus 1 minus 1 minus 1 meeting up with each other, one complex conjugate of the other. You can see that it'll give you the same calculation we got for the probability. The absolute square of that coefficient is what showed up here. But this is a sort of more formalized way of doing it. That seems like a nice, reasonable way of doing the calculation. And it gives the same answer. Again, this way works really well if you have your state on the right written as a combination, a linear combination of eigenstates of the operator, because if it is, you can just act on them directly. Now, if it's not written as a linear combination of that operator and eigenstates, it's going to be a mess. You don't know what the operator is going to do. You'll have a more complicated job in front of you. So the last thing you can do, and it's inspired by this, I'm going to erase all this because we saw it came out to the same calculation. I want to point out that we can turn this, we can take this version here, and we can take the matrix representation of this form. I can do a matrix representation and say, what is the matrix version of this whole thing? And I want to do I want to do my matrix representation in the SZ basis, and not room over here to put it in, so I'm going to do it right down here. My matrix representation is going to be, well, the matrix rep of a bra vector is a bra state is a row vector in matrix form, and it's going to be 0 for the first coefficient, negative 3i over 5 for the second coefficient, and negative 4/5 for the third coefficient. That's the matrix representation of this state because it's the complex conjugate of each one. The matrix representation of SZ hat I actually have right here. It's just this standard h bar 0 minus h bar along the diagonal. I can factor out the h bar if I want to, times h bar times the matrix 1, 0, 0, 0, 0, 0, 0, 0, minus 1, and then times a column vector. And the column vector is the representation of this psi ket, the original psi ket. That's the easiest one to write down. That is 0, 3i over 5, minus 4/5 as my column vector. This is just a matrix multiplication problem when I phrase this in that language. And the good thing here is that if we already have the matrix representations all on the same basis, then this will turn out to be a really straightforward way of doing all these calculations. Let's try it out. Let's do this calculation. So this is equal to, I'm going to do this multiplication first. And I'll factor that h bar out of the front just to make my life easier. H bar times 0 minus 3i over 5 minus 4/5 times, let me do this matrix multiplication over here. 1, 0, 0, that's just 0. 0, 0, 0 times this is 0. And 0, 0 minus 1 gives me 4/5. You can actually start to see in this calculation exactly how it reflects what happened earlier when we did this with the Bra-Ket formalism. The zeros coming into various places. When I do this, I end up getting, now I do this matrix multiplication, h bar times 0 plus 0, because it's 0 times minus 3i over 5, minus 16 over 25, and you can see that gives me the same thing, minus 0.64 h bar is my answer. So again, this method also works. So we've seen 3 ways of calculating this expectation value, depending on what data we want to use, what information we want to use about our state. The third one, in particular, we could have done regardless of whether we'd done all these calculations first or not. All right, so doing all that in the z basis was relatively straightforward because I'd specified my states in the z basis. Let me go and look at let me look at this in the y basis and ask the same questions and see what we have. Now, if I've already done the calculations that I have up here, if I've already said what the probabilities for each one of these states is, then this is relatively straightforward to do the first approach, the sort of defining approach of this. I can say, get rid of that, I can say that my expectation value of Sy is going to be h bar times the probability of Sy equals plus h bar, plus 0 times the probability of Sy equals 0, plus minus h bar times the probability of Sy equals minus h bar. And I know those probabilities because I calculated those in that previous video. I can write that down, and I'm going to get that this is h bar times, this probability is 0.6794 plus 0, because 0 times anything is 0, that one's easy to do, and then plus minus h bar times 0.06% is 0.0006. That's very small. You can see the expectation value is not going to depend on that very much. This is going to be roughly, I guess, positive 0.6788 h bar is my expectation value. That's what I come up with. Double checking my notes, so that's what I got earlier. Yep, same thing. So you can see where that came from. I've got an expectation value. The second method is harder to apply here. If I wanted to use that second method that I used, what would I have to do? I would have to say, I'd have to write this state out in the SY basis, write it out in terms of Y kets, and then act on those kets with the SY operator that knows how to act on them, and then translate that. That's kind of a pain. What would I have to do to do that? I guess what I would do would be to use these expansions in that basis to write these out. I'm not going to bother with it because that's not going to be the most efficient way to do it. Since I already know what the SY operator is in the Z basis, I'm going to jump straight ahead to our third method. I'm going to jump straight ahead to saying that my expectation value of SY is also equal to, we know it is psi SY hat psi, and that's sort of another defining way of writing this down, and I'm going to represent this in still the SZ basis, because I know the psi representation in the SZ basis, and SY is a standard matrix. That's something that we've learned in class, how to calculate the SY matrix for spin 1 or spin 3 halves or whatever. We know how to do this, so we're going to put this in matrix form, just as we did before. And doing this in matrix form, let's run through it. Let's see what that is again. So this is going to be, my row vector is the same as it was a minute ago, 0, complex conjugate, so minus 3i over 5, 4, or minus 4/5 is my row matrix. For SY, I've got my matrix here. It's a square matrix. It's not as simple as it was before, but it's still there, times h bar over the square root of 2, and it's a bunch of i's and things. 0 minus I, 0. I, 0 minus I, double check, 0, I, 0, times, and then again, my ket is represented by a column matrix, column vector, and that's 0, positive 3i over 5, and minus 4/5 is that column vector. I've got this. Again, I can just do a matrix multiplication problem at this point. So I'll factor out my h bar over square root of 2, just so I have that pulled out. So this is equal to h bar over square root of 2 times, not doing this matrix first, 0 minus 3i over 5 minus 4/5 times, what's my column vector going to be? Let's multiply this out. First row is 0 times 0 plus minus I times 3i over 5 minus I times plus I gives me 1. So that's 3/5. 0 plus 3/5 plus 0 is my first row for this. My second row is going to be 0 times I plus 0 times this, 3/5, minus I times minus 4/5 is plus 4i over 5 is my second row. And my third row, 0 plus I times, but better not be plus, I times 3i over 5 is minus 3/5 and 0. So what do I get? This is equal to, oh, well, okay. This matrix in particular, this part, just separate this out, this part is equal to 3/5, 4i over 5, and minus 3/5. 4/5 I, I guess, could be null. So that's what that matrix is going to be. And at this point, now I can do the multiplication. I can do my matrix multiplication with the row times the column I just got, and I'll find that this is, in the h bar over square root of 2 out front, times, let's multiply it out. 0 plus 3/5 is 0, minus 3i over 5 plus 4i over 5, or times 4 plus 4i over 5 is minus I times plus I is plus 1, so that's 12/5 plus 12/5, and then here minus 4 times minus 3 is positive 12 again, plus 12/5. So I get 24 h bar over 5 square root of 2. 24 h bar over 5 square root of 2. I didn't try to do this explicitly, did I? Maybe I should have. Let me rationalize the denominator, multiply by square root of 2 over square root of 2. That gives me 24 square root of 2 h bar over 50, or if I really wanted to, it's probably good enough. Now I've got that. If I plug that into a calculator, just plug in that number, it turns out that getting that gives me exactly the same probability I had before. It'll give me, because this is 48 times the square root of 2, square root of 2 is about a little less than 1.5, so 90 is 80, 87. So this will give me something like, this will give me exactly what I had before. As I'm saying this, I'm looking down and saying, yep, 0.67, yeah, same thing, 88 h bar is the answer I'll get from that. So it's actually pretty satisfying to see this come out in this way, to see that I've gotten this result by just doing matrix multiplication instead of having to do a bunch of complicated bracket calculations. All I have to do is just use the basis representation. If I know both my state vector, my psi ket, represented in this basis, and my operator represented in the same basis, I can find the expectation value of that operator entirely by doing a matrix multiplication problem, and I can dodge the need to calculate all these probabilities, which, if you watched the last video, took a long time. I think that's pretty cool, but this is how you do expectation values. There are multiple ways of doing it depending on what's most convenient for the problem you have and what information you already know. I think that's useful, and I hope it's useful to you.